Welcome to these review videos for Calculus 1. Hopefully you'll find them useful. Just a couple of preliminary comments before we jump in. Number one is that you should be trying these problems before you watch the videos yourself. That's how you'll get the most out of these videos, is by not just by passively watching the videos, but by trying them first before watching the video. So you may want to pause, you might want to just stop watching this video, go try some problems right now. You want to take a break later on and try problems by yourself. And that's how you get the most out of these review videos. Number two comment to make is that I'm assuming that you will have the review sheet accessible with you. I won't always be writing down the entire problem. I assume that you have this, that you can look at this while you're watching these videos. Okay, without further ado, let's just jump straight into the first problem. Find the slope of the line tangent the graph of this function here at x is equal to 3. This is nothing more, this is pretty much a gimme to start off with. The slope of the line tangent the graph is nothing more than the derivative. So this is asking us, do we know the derivative of y is equal to 3 log of x minus 6 square root x? Well, y is, I'm just going to rewrite the square root here as x to the 1/2 power. So we can use the power rule a little bit more easily. The derivative of natural log of x is 1 over x, and the derivative of 3 natural log of x is 3 over x. And then we'd have the derivative of x to the 1/2 will be at 1/2 x to the negative 1/2 power by the power rule. So this is 3 over x minus 3 times x to the minus 1/2 power. And at x is equal to 3, at x is equal to 3, we would just get 3 over 3 minus 3 times 3 to the negative 1/2 power. So this would be 3 over 3 is 1, minus 3 over the square root of 3. 3 over the square root of 3 is square root 3 itself. And this is a perfectly good final answer here. Okay, that's problem number one. Problem number two is asking us to use the definition of a derivative to find the derivative of this function here. So how do we do that? G prime of x, by definition, is the limit as h goes to 0 of g of x plus h minus g of x, all of that over h. Okay, so limit as h goes to 0 of g of x plus h. Everywhere we see an x, we replace it with x plus h. So this is 4 over 3 minus x plus h minus 4 over 3 minus x. All of this over h. Okay, so let's take the numerator here, combine it into a single expression here, put things over a common denominator. To do that, we're going to want to multiply this first fraction by 3 minus x over 3 minus x. We're going to want to multiply the second fraction by 3 minus x plus h over 3 minus x plus h. Okay, so the denominator of our new numerator here is going to be 3 minus x times 3 minus x plus h. And then the numerator here is going to be 4 times 3 minus x. So that's going to be 3 times 4 is 12 minus 4x. Minus 4 times this expression over here. 4 times 3 is 12. 4 times negative x will be negative 4x. And then there will also be a negative 4h there. Okay, So 12 minus 4x, distributing out this negative sign, negative 12 plus 4x plus 4h. All of that over 3 minus x times 3 minus x plus h. All of that over h. Okay, now is the point where we should be looking for some cancellations to happen. Those 12s cancel. Those plus and minus 4x cancel. And so then we're just left with a 4h upstairs. Let me just recopy this. 4h over, I'm going to move the denominator of the numerator and the overall denominator to the same line. We can do that. And now we can cancel out those h's. Okay. So what are we left with? We're left with the limit as h goes to 0 of 4 over 3 minus x times 3 minus x plus h. And at this point then we're taking the limit as h goes to 0, x is staying put. Limit as h goes to 0 here. And so the only change we have to make is replace h with 0. So 4 over 3 minus x times 3 minus x plus 0. This simplifies as 4 over 3 minus x, quantity squared. So I think this is a good exercise to work through this. Lots of good, useful, typical algebraic manipulation here.